Okay, so let us talk about the 5.1 sequences. So let me write down sequences. Sequence definition is a function whose domain is the set of positive integers. Not real numbers, okay? Positive integers. So look, we're gonna start integers, positive. So we have a number line, middle one is 0, and then positive integers and negative integers, right? Okay, start one equal to, we give it to a sequence like this. And then the function, so we denote the function notation like that. And f of n equal to a sub n, all right? Now we called all the sequence here, a sub 1, a sub 2, a sub 3, and so on until a sub n, right? So we call these terms of sequence, terminology, right? The number a sub n, it's a number, we get the number, right? So the number a sub n is the nth term. Another terminology, terms. And this one, nth term of the sequence. Okay, let me bring how it looks like a sequence screenshot. So, oh, where it go? Oh, it's gone. Oh, right there. So this one. So sequence like that. So this is a 2 to the n. Then look, if we have the sequence 2 to the n power, right? Then f of 1, which is, so f of n equal to 2 to the n. Then 2 to the 1, which is 2. So we get order pair like 1 and 2 here. And one, when n equal to 2, then 2 squared, which is 4. So 2 and 4. Yeah. So it's like that, right? Can you see that? But it's in the dot, not the real number. So let me show you, compare with what we did as a function 2 to the x power, right? So here. Oh, not this one, this one. I did not use the cut. So compare with this one, compare. We have f of x equal to 2 to the x power, right? So the domain for this one, oops. Okay, this one. Or the real number, right? The function for the exponential function, right? And then sequence, the domain is positive integers. Can you see that? That's why they must have an order pair everywhere here, right? So when you draw the graph, we have an order pair, so we make a dot. But later on, we connect everything because their domain is the real number. We connect each other, all the dot, right? The sequence, that their domain is positive integers, so we have only dot like that, okay? We can have more, right? All right, now, in the sequence, we have two types of sequence. One is a arithmetic sequence, one is geometric sequence. So geometric sequence, we talk later sections. So here are two types. Arithmetic sequence. Let me use it here. So the difference between every pair of consecutive terms is the same. Okay, so for instance, they give us 3, 7, 11, 15, 19, and so on. So they're using dot, means that keep going. All right. So we call this is the sequence. Moreover, more detail, we called arithmetic sequence, but we not really called the arithmetic sequence, just a sequence. All right. Okay, then the first one we denote this is a sub n. I'm sorry, a sub 1. And second one we called a sub 2, right? And third one we called a sub 3, a sub 4, a sub 5, right? So look, we can create the formula. Okay, so look, a sub 1 equal to 3. Now we can say that a sub n equal to a sub n minus 1 plus 4 for n is greater or equal to 2. So we call this is the terminology, which is recurrence relation. Let me write down. So recurrence relation, let me write down one term or more.
Is recurrence similar to recursion, or is that something?
Yes, right. That's
okay.
correct.
Oh, it's like recursion. Okay.
Recurrence, yes.
Thanks.
You're welcome. Relation. It's a one term or more of the sequence. Is given explicitly. And subsequent terms are defined in terms of earlier terms in the sequence. Okay. All right. So let's say that we have a sub 1 equal to 3, right? So let's say the a sub 2. A sub 2, which is a sub 2 minus 1 plus 4, right? So a sub 2 minus 1, which is a sub 1 plus 4, right? Then a sub 1 was a 3 and plus 4, which is a 7, which is a sub 2. Very good. Thank you, right? So let's do a sub 3. So a sub 3 means a sub 3 minus 1 plus 4. That is a sub 2 plus 4. Now, this is a sub 2 actually, right? So a sub 2, which is 7, plus 4, which is 11. That's how we get the a sub 3 under there, right? Okay, so we called recurrence relation, and then your classmate said the recover, how pronounce recoversely, right?
Recursion?
Recursion, yes.
Yeah.
Okay, it's the same. So means that the first one they given, right? The second one we repeat by using that, okay? For the previous one, all right? Okay, now we have explicit the formula. So look, this is a recurrence relation now. Explicit formula. Okay, so look, we have 3, 7, 11, 15, 19. Then we can create, so start the 3, right? Now then we can say that it's increased by 4, right? But then look, we can create this one, n minus 1. All right, so let's do this. So we have 3 plus 4n minus 4, which is 4n minus 3, right? Minus 1, sorry. Okay, let us do this. When n equal to 1, for 1 minus 1, what do you get?
Yes.
It's a 3.
4 and 1, 3, and 4 and 2, 7.
7. So n equal to 3.
11.
It's 11, right? So n equal to 4.
15.
15. We can go more further, right? Okay. And now, now this is, we can create their formula by using the sequence, all right? And that one was about what is called arithmetic sequence. Okay, so arithmetic, like a plus minus. Okay, geometry sequence. So this one is the ratio of every pair consecutive terms terms is the same. Okay, so for instance, we have 2 for the first one, second one negative 2/3, third one is 2/9, and minus 2 over 27 and 2 over 81. We can go more further. Now, recurrence relation in this case start to 2. So a sub 1, they start to 2. A sub n, which is we have a negative sign, second one, and 1/3. And we can say that times a sub n minus 1 for n is greater or equal to 2. So let's take a look. So a sub 1 equal to, check, 2. A sub 2 equal to negative 1/3 times a sub 2 minus 1 equal to negative 1/3 a sub 1. A sub 1 was the 2. So we get negative 1/3 times 2, right? Which is negative 2/3. A sub 3, can you please do that? Negative 1/3 times a sub 3 minus 1 equal to negative 1/3 times a sub 2. A sub a sub 2. A sub 2 was negative 2 over 3, right? So it's a negative 2 over 3, which is positive 2 over 9. Is it? Yes, right? Okay. So we can do more, right? So, all right. Now, explicit the formula for this one. Look, can you see that everything is 2? So we're gonna make a 2. And so a sub n equal to, and can you see that there is a negative 1/3, positive 1/3, negative 1/3, positive 1/3, right? So we make that. It's okay, thank you. So negative 1/3. Now, the power, let us do n minus 1, okay? So let us practice for this one. Let's do, check a sub 1, which is 2 times negative 1/3. 1 minus 1, which is 0, we get 2, right? A sub 2, which is 2 times negative 1/3. 2 minus 1, which is negative 2 over 3. We got that? The same thing? We can check here. Yes? Okay, a sub 3, we have 2 times negative 1/3. Then we have what is called 3 minus 1, which is squared. 2 times negative 1/3 squared, which is, it's a positive 19, right?
Yeah.
So 2 over 9, okay? Okay, so basically, this one increased by the power of 1 every term, right? Can you see? Okay. Now, let us find explicit formula here. Find explicit formula for nth term. So nth term, we are using just x sub n, right? Nth term of the sequence. The first one, we have negative 1/2, 2/3, negative 3/4, and 4/5, negative 5/6. Okay. Denominator. Something increased by 1, right? Numerator. Something increased by 1, but there is a sign. Sign change that, right? So sign change we can express as like this. A sub n means that nth term of a sequence, right? So we denote nth term of a sequence like this, okay? Now, equal to the sign alternatively change. So we say that negative 1 to the n power, then n is positive, then we get the positive, n is negative, we get the negative, right? All right, then 1, 2, 3, 4, 5. So we're gonna make times n. And then if we say the n for the 1, 2, 3, 4, 5, then the denominator will be n plus 1, right? Okay, let's check that. So n equal to 1, then that's negative 1 over, oh, it's a 2, right? Good. N equal to 2, then 2, it's a positive, so it's a positive 2 over 2 plus 1 is a 3, right? And n equal to 3, then we have negative
-3 divided by 4.
4. Okay, good. Okay, so and so on, right? Good. Now, second part, we have 3 over 4 and 9 over 7, 27 over 10, 81 over 13, and 243 over 16. Okay, what can you recognize the numerator?
There's something like exponential going on here.
Yes, and the exponential going on, which is 3 to the n power.
Yeah.
Okay, very good. Now, denominator, it's hard to say, right? So denominator, let us practice. Okay, so
Just 10 plus 3
3n
plus n.
plus 1.
Yeah.
Okay, very good, because this one comes from, look, the denominator, think 4 plus, start to 4, okay, and 3. Then we're gonna say that n minus 1, okay, then 4 plus 3n minus 3, then this will be 3n plus 1, okay, so let's check that. N equal to 1, so 3 over 3 plus 1, which is 4. Good. N equal to 2, 9 over
7.
7. Good. N equal to 3.
27 over 10.
Okay, good job. Okay, let's move on. Very good. Now, let's do one recurrence relation because we did earlier. So. Recurrence. Find the explicit formula for the sequence. All right, so we have a sub 1 equal to 2, a sub n equal to -3, a sub n minus 1, 4, and go at O equal to 2. Okay, so let's expand a sub 1 equal to 2, a sub 2 equal to -3, a sub 2 minus 1, that is -3, a sub 1, that is -3 times 2, which is -6. Okay, let us do a sub 3. -3 a sub 3 minus 1 equal to -3 a sub 2 minus 1 equal to -3 a sub 1. I'm sorry, I made a mistake. Cannot be 1. It's a 2. Then -3 times -6. A sub 2, which is -6, right?
Wouldn't the answer be 18?
Positive 18, yes. Okay.
Yeah.
All right. All right. A sub 4, which is -3, a sub 4 minus 1, which is -3, a sub 3 equal to -3 times what is called a sub 3, which is 18.
Yeah.
Okay.
-54.
Negative.
-54. All right. So we need to find the formula like earlier, like this. Then it's better we have a nice form. So look, I want to switch that -6 as -3 times 2. -6. And 18. I want to do that. 18, can I do that? -3 times -3. Times 2? Is it correct? Can you please calculate this one?
Yes, it's 54.
Is it correct? Okay, good. All right then, look, this will be -3 to the squared times 2, and this will be -3 to the cube times 2, right? All right, so then this one, do you agree? We have a sub n, which is the formula for that. Then 2 times, so every term has 2, so 2 times and -3. And we had the experience, right? So increase by 1, the power, we had n minus 1 earlier. Okay, then let's check that. So a sub 1 2, -3, 1 minus 1, which is 0. So that's the 2. A sub 2, which is 2 times -3. 2 minus 1, which is 1. So we have 2 times -3, right? Now a sub 3, which is 2 times -3 to the 3 minus 1, which is squared. So 2 times -3, -3, which is squared. Okay? All right. Okay, let's talk about the limit. Limit of a sequence. So we had a limit in the calculus 1. Limit means evaluate the function at the point, right? Now we do limit, we're gonna find the limit of a sequence, right? So sequence is, we have a function, but their domain is the positive integers instead of real numbers, right? Then we can just think about, oh, same as real numbers. Then that is working perfectly fine as well. Okay, so sequence, their domain is a positive integer, but then when you talk about the limit, it equals the same concept, all right? It's a calculus 1. All right, so we have, let me see. Find the limit. Let me denote this way because they don't say that here. So A. Find the limit of. First one, limit n approach to positive infinity, 1 plus 3n. Okay, so when n equal to 1, then it's a 4. When n equal to 2, it's a 7. When n equal to 3, what do you get?
10.
10, and so on, right? What do you think about this one then? When n approaches to positive infinity, what's the limit of this sequence?
Positive infinity.
Positive infinity, because number getting bigger, right? Can you see that? Okay, so number is getting bigger. Okay. Second one, we have limit n approach to positive infinity. So we have 1 minus 1 over 2 to the n power. Okay, so when n equal to 1, we get 1 minus 1/2, which is 1/2, right? When n equal to 2, then we have 1/4. So we get the 3 over 4. So when n equal to 3, what do you get?
7 over 8.
7 over 8, good. And so on, all right? So what do you think about this one?
1.
It's
0. Oh no, 1. Yeah.
It's a 1, okay? Why? Because this one is getting smaller, right? So this is going to 0, right? So going to the 1. Very good. 0. All right. So 1 minus 0, which is 0. All right. Okay. We have -1 to the n power. So look, this one, the limit. When n equal to 1, we have a -1. When n equal to 2, we get the +1. When n equal to 3, we get the -1. When n equal to 4, we get the +1. So what do you think about this one?
It's on a limit between -1 and 1.
Yeah, between -1 and 1, so we not really cannot say that, right? So does not exist. Okay, all right. The last one we have the limit. When n approach to positive infinity, we have -1 to the n power over n. So this one will be when n equal to 1, it's -1. When n equal to 2, it's positive. When n equal to 3, it's negative. When n equal to 4, it's positive. So what do you think about this one?
Oh, it's is it approaching 0? Or
But
does that not exist?
It's approach to 0 because number getting smaller. Yeah.
Because they're even the negative numbers are also getting closer to 0, huh?
Yeah. So so look.
like if
Let
you
me show
put
you.
0, it will be like
Yeah.
you
So
will
let me
broke
show you the
Maxwell.
picture. Okay. So this is going to 0. Okay. So let me show you the picture here.
Sure. What are you doing?
So this one. Thank you for letting me know. Okay, so look, the last one we had -1 and then +1/2, -1/3 and then +1/4, -1/5 and then +1/6, right? Okay, so look, that is the start. -1, +1/2, -1/3, +1/4, right? -1/5, +1/6, -1/7, +1/8, like that, right? So getting close to the 0 here and getting close to the 0 here. Make sense? Very good. Okay.
Yes.
So this one, they just make a dot because of sequence, all right? So better idea with the picture, right? So this one goes to infinity, or the dot, right? And then second one was going to 0. So here is the 1. So this dot going to the 1, right? Okay, approach to 1. All right, so C, the third one, -1, +1, -1, +1. -1, +1, -1, +1, -1, +1, -1, +1. Alternatively goes to -1, +1, -1, +1. Oh, this is dance. -1, +1, -1, +1. Okay, so you guys understand this one, right?
So when you like evaluate like a limit like graphically like this, you're always reading from left to right. Is that right?
What do you mean left to the right? Because yes, but sequence is yes, left to the right because positive integer for the domain.
Yeah, okay.
So, yeah, we're not using in the real numbers, right? We're not using this part because negative part, right?
Yeah. Thank
Okay. only positive. Thank you. All right, then definition we have, let me write down. We have convergence, then we say that the limit goes to the number, okay, which is the L. Let me write down. Let me just make it short. Okay, so we have a convergent sequence. Okay, so when is convergent sequence and L is the limit of the sequence. Then we can say the limit when n approach to positive infinity, okay, then a sub n equal to L. The sequence is not going to converge, it's not the number, then there is a positive infinity, then negative infinity, we say the divergent sequence, all right?
What does L represent?
Just number.
Okay. Thanks.
Here we come. So in this case, L equal to 1, right? In this case, the L, the limit approach to 1. In this case, the limit approach to 0. Yeah. If a sequence A sub n is not convergent, see divergent sequence. Okay, so I said earlier, we can just think about the sequence as the function of the real numbers, even though they say that this is the domain of positive. So when you talk about the limit, because of this reason, okay, so let me write down limit of sequence defined by the function. So let me just write down. We have the function limit x approach to positive infinity, like calculus 1, right? And the limit exists, then the function of limit goes to L, right? Then we have a convergence of the sequence. Is the band converges. Then we can say that the limit n approach to positive infinity is the band goes to L as well. Okay. Let's see. So we're gonna use the same limit law as calculus 1 in the sequence as well. So let me bring the law here. So we want to take the limit and approach to positive infinity. Then we have a constant. This is the constant. Then what do you get? We can see the constant, right? So for instance, we had think like x approach to 2, right? So what do you get? This one.
3.
It's a 3. It's a constant because there is no x, so we don't apply. We cannot apply the limit when x.
Is
approaches.
it calculus 1?
Yeah, it's a calculus 1, right?
Oh,
We
yeah.
are using all the laws into the sequence as well, right? Same, exactly same. This one is the same. We just change the n approach to positive infinity, right? And we have a constant. Then we can take out this constant out of the limit. Okay, we learned that from the calculus 1 as well. This is the sum of limit and difference over limit. We split like that. Okay. Then since they have a limit exists, which is a, which is b, and they have a and b there. Okay. Multiplication rule, we can split as 2 terms, not terms. We're not supposed to say term because of multiplication. We can just split one and the other, right? So we get that. And quotient rule, same thing, okay? Then we have a over b, but the denominator cannot be equal to 0, all right? So we are using same law for the limit in sequence as well, okay? All right. So let us do this one. Determine whether or not the sequence converges. If it converges, find its limit. Okay, so this is what I did in the calculus 1 today. 5 minus minus 3 over n to the second power. Okay. So what do you think? We can apply the limit, same as the calculus 1. Let's say that we have a limit n approach to positive infinity. So we can say that, but then this one we can express 2 terms. So and approach to positive infinity, we can split 2 terms. But then coefficient in front of, I mean in there, coefficient, right? This one, we can take out, right? By the second law, right? So we can take out that. Okay, then what do you get this one? When n approaches to positive infinity, what do you get the constant? Someone has the very bad internet connection. Let me mute everyone. And then if you want to talk, please unmute it for yourself. So mine is not mute, right? Okay, so please talk.
5.
5.
5, very good. It's a 5. Now, what about this one?
0.
When n, oh,
0.
it's a 0, very good. Okay. So what do you get then?
5.
5.
5, very good.
5.
Good job. Mhm.
Miss Lee, so that is the first rule. That's the
Uh,
number 1.
Okay, I'm using this one by first. And this one by second. Okay. And you might think this one one over n times 1 over n. Okay. That is multiplication by 3. Right? So we can say that we can split one multiplication, another one. Then we get 0 times 0, which is 0. You might think that way, okay? Or we can think about the graph, right? Think x squared graph, right? Yeah, parabola open upward, right? Then when x approach to positive infinity, then the graph goes to positive infinity. So we not usually include this one as a step. Casually, we say that 1 over infinity, what do you get? Is 0, right? That's how we learned from the
Yes.
calculus. Yes, thank you. Okay, 1 over infinity. So 1 divided by a huge number, millions, then 0.000001, right? Okay. All right. Second one. We have 3 to the n to the 4th power, 7 n squared plus 5 over 6 minus 4 n to the 4th power. Okay. Look, I'm gonna give you a tip. Take highest power from numerator and denominator. Okay.
It's like a alphabetical rule.
Not yet. So the highest power will be 3n to the 4th power from the numerator. And denominator will be negative 4n to the 4th power, right? So we can simplify. So then we get limit n approach to positive infinity. We have a 3 over negative 4. What do you get this one?
3, 4. A negative 3, 4.
Negative 3 or 4. Very good. Okay, so this is my tip. All right, how about the third one? Now, your classmate mentioned the L'Hopital rule. Yes, we're gonna use that. So we have 2 to the n power over n to the 2nd power. Okay. Look, think about 2 to the x power. Then this one looks like that, right? So when n approaches to positive infinity, this one goes to positive infinity, right? So we have a positive infinity. And n squared, what we just did here, n squared, think about x squared. So when n approaches to positive infinity, then the graph goes to positive infinity as well, right? Then look, we get infinity over infinity. Okay. Now, then it's indeterminate form, right? Then your classmate to say that, oh, we can use the L'Hopital rule, right? All right, so in order to use the L'Hopital rule, we have to have a function with the real numbers because we must be continuous, right? So derivative must be continuous. So we're gonna change that as a function notation. So let us do this. F of x equal to 2 to the x power over x to the second power, okay? Now, indeterminate form. We can use the L'Hopital rule, right? So that is with derivative, numerator and denominator separately, respectively. All right, so you might not remember because your professor said, oh, don't remember for this one, right? Okay, so this means 2 to the x with derivative ln with the base, okay? Okay, then over x squared, you know how to do it, x squared, how do you derivative?
2x.
Yes. X.
2x, good. All right, now ln2 is the number, so we might think the limit, oh, did not put the limit. And when x approaches to positive infinity. Okay, so this is the number, look, this is 2 to the x power, which is infinity over x, like this, straight line. So straight line, like that, right? So when x approaches to positive infinity, also goes to positive infinity, right? So this is also infinity over infinity. So indeterminate form again. Then we can do L'Hopital again, right? So we have a limit when x approaches to positive infinity. Okay, now we do derivative 2 to the x power ln2 all over 2x. Okay. We do derivative. This is a number, right? Number, we can take the number out. Now, we do derivative of this one. That is, oops.
2x ln to the second.
Yeah, so we have 2 to the x, ln2 again, right? So we're gonna make squared. All right, good. All over. How do we do denominator? Derivative of
Just
2x? 2, good. Okay. All right, so let us do this. ln2 squared, which is number, over 2, which is number. We don't care about that. Look, when x approaches to positive infinity, what do you get is? 2 to the x power?
Infinity.
Infinity, okay? So we get the infinity then. All right. Okay, let's move on.
I have a question.
Go ahead.
If you're doing like this last step and you figure out that the denominator is going to be a constant, does it even matter what the derivative of the numerator is?
In this case, does not matter because we have infinity. Infinity is a huge number. So the tiny number 2, tiny number 3 does not matter. Okay? Make sense?
Yeah, it's interesting. Thanks.
Okay. All right. Now let us do third one, and then we do couple the cosine sequence there. So let us do this one. All right, so we have one plus 4x, 4n. To the n power, right? Okay, this problem, let's see, when n approaches to positive infinity, so we have a small tiny number divided by the huge number going to the 0, right? So then 1 plus 0, which is 1, and then n approach to positive infinity, so we get 1 to the infinity, right? Which is indeterminate form again. Now, we can use a L'Hopital rule, right? So in this case, what we do, we're going to change it as a function. Okay, look, we have x on the power, then we did this one in Calculus 1. You might not remember, that's fine. Okay, so let us do together. Let's say that we say that y equal to 1 plus 4 over x to the x power. Okay, now since we have the exponent there, so we take the ln both sides to bring down the exponent, right? So we take the ln. So let's do that one step. Okay, now, oops, I totally forgot limit. Happened all the time. Okay. So start to limit x approach to positive infinity. Okay, then I can switch it over. So I want to make it a little bit nicely. Yeah, I already have one. Normally we have to make x is outside, one step more. Because since I made a mistake, normally x was the, let's just follow the steps. Equal to x limit x approach to infinity. Now I want to change that order, so we will have ln y equal to limit, and then I want to insert x in there, and then ln 1 plus 4 over x. Okay. All right. Now what we do? Look, when x approaches to positive infinity, what do you get this one?
Positive infinity.
It's go to the 0, right? Okay, so tiny number divided by huge number is 0, right? Then we get the infinity there. So yeah, it's okay. Infinity times 0, right? So we get infinity times 0, which is indeterminate form. All right, then we're gonna make a nice form in order to use the L'Hopital rule. So we will have, look, I'm gonna see. The left side is still there, and the right side we will have. Do you agree with this one? I have to write down the limit. I still kept forgetting. Yeah, do you agree with this one?
Looks correct, yes.
Yeah. Okay, then ln1, which is 0, then the denominator, which is 0 as well, when x approach to positive infinity, right? Okay, now we can take the L'Hopital rule, right? So how do we get? So ln 1 plus 4 over 7 ix 7 and derivative one over x. Yeah. Okay. What do you get this one? Numerator with the derivative? We have a what is called, we have expert with the derivative. With the derivative, what do you get?
0.
Derivative? How do we derivative ln x?
1 over s.
1 over x. Then how do we derivative of this one?
Oh yeah, it will be 1 over x.
So whatever, everything, we get that, right? And then we make a chain rule. Yes? Okay. What's the derivative of this one?
ln
We do derivative, not the integrate.
oh
Negative
1 over x squared.
Negative 1 over x squared, right? Okay, then what's the derivative of this one?
what, sorry?
What's the derivative of this one? We're gonna make a chain rule, please.
negative 4 s
Negative 4 divided by x to the second.
Okay, then looks like this one is canceled out, right?
Yes, we can.
Yeah, right? So looks like it. Oh, yeah. Rushing. Okay. All right, so this one cancel out, right? With the negative, right? So we will have 4 over 1 plus 4 over x squared, right? Okay, now, oh, sorry, there's no squared. Okay, when x approaches to positive infinity, what do you get?
4.
We get the 4, right? So this is a 4. All right, so we have the left side, we did not do anything, ln y there, right? So ln y equal to 4. Now we take the e both sides to get rid of the natural log, right? So take the e both sides. So then we get y equal to e to the 4th power. Okay, but then what was the y? Y equal to, we set it up, limit of the function. So can you see that? Y equal to that. So come on, let me copy. Copy. So we said that y equal to the, okay, equal to e to the 4, right? Okay, now we can say that the sequence converges to, because e to the 4th power is the number, right? So the sequence converges to e to the 4th power. What's the approximately e to the 4th power?
Like 2.7 something.
To the 4th power?
Oh, to the 4th power. Oh, I don't know. I have my calculator.
Let us calculate it. Give us a second.
I forgot where the E button is on my calculator.
Okay, so whatever, right? Oh, 54, thank you. 54.598. Thank you so much. All right, so look, let me give you a tip. We learn from the Calculus 1. So Calculus 1, we have had limit when x approaches to positive infinity, 1 over x to the x power. So we had this is e. E means e to the 1st power. Okay, now can you see that? There is 1, which is e to the 1st power. Look, can you see that there is a 4 e to the 4th power? Okay, so every time we have this form, which is, let's see, if we have question, if we have x approaches to positive infinity, 1 plus, let's say, pick a number.
8.
8 over x to the x power, then what it will be?
E to the 8.
Yes. Okay, this is my tip. All right. Good. Okay.
And we don't have to share our work for that. Just we can just put that answer in.
Yes, this is a calculus one. Okay. All right, so let us do one problem. Then we are done. Determine. We have cosine 3 over n squared, whether converges or not. If it converges, find its limit. Okay, so we have a limit when n approaches to positive infinity, cosine 3n squared, what do you get? When n approaches to positive infinity, what do you get? This one?
Infinity.
dt.
Okay, you talk about the one this one is equals to infinity, good. So 3 over huge number, what do you get?
Yellow.
0, okay. And what do you get cosine 0?
1.
1. And what do you get this one?
Just one.
1, right? So it's converges. All right, and then converges to the 1. Converges to 1. How about that? All right, thank you for coming.